A very good afternoon to all of you. So, in today's class, we are going to discuss bipolar pulse width modulation. Okay, so till this point, we have covered square wave inverters, half bridge square wave inverters. Okay, after that, we covered full bridge square wave inverter. The square wave inverters are subjected to various kind of loads. For example, R load, purely L load, RLC load. Okay, and the waveforms were obtained for this part. Okay, second very important thing is that the drawback. The square wave inverters are having its own drawbacks. Okay, and that needs to be understood very carefully. Yes, their drawback are quite prominent and that needs to be explained very carefully. First drawback of a square wave inverter is that there is no room for voltage regulation. Are you getting it? Yes, it means the output voltage will remain VDC. It will remain VDC. It cannot change. Okay, in case of a square wave inverter. But because you can see from here, I would like to elaborate this point because this is often doubtful, that this is 4 VDC by n pi sine n omega naught t. This is a summation n equals to 135 to infinity, where n is the number of harmonics. This is n, and we can very well understand that this waveform sinusoid is the fundamental of this rectangular pulse. So every time the output will depend on the value of VDC. The fundamental will depend on the value of VDC, that is 4 VDC by pi upon root 2. So, and VDC is fixed. For most of the inverters it is fixed. VDC is fixed. We cannot change this part. So the peak value can't be adjusted. The fundamental output value of the inverter voltage can't be adjusted. But if we look at the methods that how we can lower this value. So the scientists developed their science and they gave a conclusion. They explained that if various researchers came to the floor, okay, and then they derived a technique in which when we do one switching in one half cycle, look at this, that is, if one half cycle one switching is performed. Okay, so if one switching is performed in one half cycle, then we can be very sure of one thing. What is that point? That point is that this negative voltage will cause the overall fundamental to dip. Are you getting it? Because if you divide this in one period, so in this period the average positive value has reduced from this part. This is complete VDC, but now it has reduced. Similarly, that switching can be carried out in the negative half and it has also reduced. Okay, so from here we can draw this conclusion. Have a look at this part. Yes, these are the waveforms which can be very carefully looked into. Look at this. This is one switching, this is another switching, and in this switching this is the sine wave. Okay, now if we perform two switching in one cycle, then obviously this sine wave, the amplitude of the sine wave will reduce. Clear? Again performing one more switching, this will reduce further. So by increasing the switching, by controlling the switching, we are controlling the amplitude of the fundamental output voltage. I think this crucial point is clear to all of you. If this point is clear, then I can move on to the other point. The second problem with sinusoidal PWM inverter is that the THD is 48.43. It is very high. Or we can say in very simple languages that the lower order harmonics are predominant. For example, have a look at this. N equals to 3, 5 all are present. Okay. So what this PWM will do? This PWM will shift these harmonics. Okay, this is I am telling you in advance that sinusoidal PWM will give us the voltage that is MVDC by sin pi. Okay, and it will be a sine wave. So what will happen is that the lower order harmonics are shifted to the higher side, and when they become higher order harmonics, then their filtration becomes very easy. Those harmonics can be filtered out very easily. We need not to carry on. We need not to add extra filters. Okay, because as the frequency is lowered, then the filter size will be greater. Now, have a look at this. This is the basic waveform. How a staircase sine wave is created. Now I am going to show you this part. Okay, look at this. What I am doing is that, suppose this is one period. Okay, try to understand, this is one period. This is the on duration, this is the off duration. In the second period, again this is on duration, this is off duration. On duration is increasing subsequently. In the third time period, the on duration has increased a little more. I think it is 50-50. Similarly, in the next duration, the on duration is greater than the off duration. Is that clear? I think this point is clear. And this is a very, very important point. If this is not clear, then you people are going to stuck. So this should be very clear. Now have a look at this. What will happen? Pay keen attention to this part. So in this cycle, this is the voltage level that will be obtained. For this cycle, this is the voltage level that is going to be obtained. In this cycle, this is the voltage level that is going to be obtained. In this cycle, this is the voltage level. So we can very well say that on moving from this side, the voltage levels are increasing in steps, just by merely controlling the on duration of switches. Is it clear? I think it is clear. Now the issue arises, these steps in practicality these steps are reduced to very small size. So this is their actual side. Look at this. Small and going like this. Okay. So this is, now if you look into this part, then it will look like a staircase. But if you zoom out, for example, have a look at this. I am showing you this. This is the steps. These are the steps. Okay. But when we are zooming out, then it is going to resemble a sine wave, a stepped sine wave. So this is the beautiful concept of sinusoidal PWM. I think this point is quite clear. The understanding is good. Now there comes a drawback, a very good thing, that two kind of PWM are possible, that is unipolar and bipolar PWM. What happens in unipolar is that the pole voltage will be completely positive or zero. Okay, and in the other part, when the sine wave is going to in the negative direction, the pole voltage will be going to get negative. So it is either negative or it is zero, again negative or zero, negative or zero. But if we look at the bipolar part, have a look at this bipolar part, then we can very easily draw this conclusion that in the bipolar part, the pole voltage is positive for a duration and it is also going to be negative. Okay, but for the positive voltage, the on duration is greater than the negative part. Is it clear? I think the understanding, the difference is clear. More upon this will be followed up in the next lecture. Thank you. Have a good day.